So everybody, welcome to the math club for today. Thanks for, uh, I've got kind of a talk that I think is kind of fun. And maybe I might embarrass myself in front of Neil because he might know even more tricks than I do. But I'm going to talk about, see if I've got this right here. All right, so I want to talk about some math tricks that I think are kind of interesting. This is certainly not an exhaustive list because there's math is full of things that look like magic, and in a certain sense maybe are kind of magic, but of course there are reasons behind it. So let me start you off with one. This is not a cool math trick. And in fact, I'm embarrassed to kind of put this up here, but so for example, but I'm willing to bet that if you've ever taught math, you've seen this done. Cancel the sixes and you get 4, right? This is not a trick, and this is, I'm not even comfortable having that on my board, right? So I'm going to get rid of that. But, canceling the sixes, I'm sure we've all seen this kind of thing before. There's no mathematical reason for that. That's kind of a trick. So what I'm going to do is I'm going to show you some stuff from various sort of walks of mathematics that are kind of neat tricks that to me are kind of interesting that they work. We'll talk a little bit about why they do. So the first one that I'm going to talk about is the square root of. And actually, I'm curious if anybody has seen this. I think Neil is kind of a sort of a fan of this sort of thing, so perhaps he's seen this as well. My dad actually showed me, and my dad is but a lowly architect, and he showed me this actually when I was in 7th grade, and it was something that he had learned in grade school many years ago. So here's what you do. Take a positive integer. So I'm going to take something like, I don't know, 227. Suppose I want to find the square root of it. Well, put the decimal point here, and then put groups of zeros. Just group things in 2s on both sides of the decimal place that you like, because this could even be a decimal expansion if you like. I'm going to sort of mark this off because these come in pieces here. Now, you start with an honest to goodness square root. What's the nearest, what's the square root of 2 sort of rounded down? Well, because you can't go over 1. Now, here's where it gets kind of weird, this algorithm, because what you do is you're going to subtract just like you did, so 1 squared is 1, and you subtract, but then you drop the next 2. It's sort of like long division, except instead of dropping the next 1, you drop the next 2. Now, whatever you've got up here, double it, and leave this blank, because I'm going to change this later. So this is going to be 20 something. How many times does 20 go into 127? Well, it looks like it goes in about 6 times. But it's actually a little bit less than that, because whatever I put here, 5 must go here. So whatever I put there goes there. So 5 times 25 is 125, and that's as close as we get. Now repeat the algorithm. You subtract, and then you drop the next couple. Double 15, blank. How many times does 300 and something go into 200? It doesn't. So it's a 0, subtract, and drop the next 2. So let's see. We're down to this now. Okay. Double up on this, you get 300. How many times is 300? Well, more or less, how many times is 3 going to 20? This looks like it'll fit about 6. And so this is 36, 0, 18. So notice this is getting more of a pain to do. 64, that's a 0. So that's 64, 9, 1. Now, one final step, you double this. This is 30120. Bring down the next two zeros, etc. And so it looks to me like this will be about 6 as well. Right? And you just continue this process. Now, check this on the calculator, and you will see that you get this right. Let me do one that's like more familiar. Square root of 3, for example, is probably familiar to a lot of you because you see the square root of 3 over 2 in trig all the time. Square root of 3, like this. We'll get the first few decimals out of this. Nearest square root of 3 without going over is 1. Drop the next 2, 2 blank. How many times does 20-something go into 200? This time it's going to be 7 because I got to replace that by 7, 189. Drop the next 2. I get 3, 4 blank. How many times should 300 go? That's about 3, I guess. This is 9, 1029. Drop the next 2. That's going to be 346 blank. That looks like an easy 2. 4, 12, 60. Well, I guess it's 69, isn't it? 76. Next 2, double up, 34, 64, blank, and so forth and so on. That looks like about a 5. Let's test this last one to see if 5 works. 5, 12, 2, carry 3, 3. Whoops, I'll count 5, 2, 2, 23. I seem to be, did I do that wrong? Maybe this doesn't fit. Oh, this is too small, isn't it? So I guess that's a 0 actually. I've got this off by 1. But anyway, you can check me, make sure it's a 0 and I didn't make a mistake. But this algorithm always gives you the next correct decimal place, the square root function. I'm curious, how many of you out there have seen this before? Anybody seen this before? Okay, yeah, Neil. I had a feeling maybe Neil had seen it, but that's about it. You can find this. I am something of a collector of old math books. And if you look in like these ancient antiquities, they teach kids how to do this way back when. You would see why people don't teach it anymore, right? Because scientific calculators, computer algebra systems, why would you teach this to somebody? The other reason that you don't teach this to somebody as well. So I'll tell you a story about this. My dad taught me this algorithm, like I said, when I was in 7th grade. When I was a first-year graduate student, I showed this to some friends. We were mucking around in the up in the cubicles, and I showed this to them, and they were like, "You are so on drugs. There's no way this works, right?" And actually, I won a bet because we sat down and we actually proved that it worked. But when I showed this to a friend of mine in physics, he said, "Oh, this must be equivalent to Newton's method." So, is it? Is this Newton's method? Is that where this comes from? So let me take you on an excursion back to calculus. How many of you remember Newton's method? Anybody remember that whole thing? So it's kind of a neat little trick for finding roots of. It's ingenious, but it's a trick for finding roots of functions that are at least nice enough to have a derivative. And so if you wanted to find the square root of a, then you would consider that this is a root of x squared minus a. And I can draw this function with something like this. And here, the x-coordinate here is radical A. Right? Well, what Newton's method does, in a very ingenious way, is you start at some point. It doesn't matter so much, but you should be reasonably close to the root, but you can do this by using like the intermediate value theorem or something like that to get something that's reasonably like the nearest integer to a root. Of course, I can make pathological examples where this doesn't work very well, but here's the trick behind Newton's method. Wherever you start, and we'll start on this side so that we're going to converge this root. Start with your initial guess x1 and find the point on the curve, x1, and in this case, x1 squared minus a. And then draw the tangent line. This gives you your second estimate. Right? And now your second estimate, you draw the point on the curve again and do its tangent line. And it comes down here, say to x3, and then repeat the process, x4, and so forth. And you can see intuitively that this seems to converge to the root, square root of a. And in fact, it does so, and it does very nicely for this function. Now, given that picture, can somebody tell me why this is not Newton's method? Anybody? Well, what this algorithm does, if you believe me, is it gives you the next correct decimal place of the square root function, right? So this is getting closer and closer to the square root of 227, but it's coming in from below, right? Because you always get a little positive action every time you continue this algorithm. This, on the other hand, if you look at it, in fact, I started with an estimate that was too little on purpose, but you can see what happens is the first estimate kicks you above the root, and every other estimate after that will be above the root. So Newton's method actually converges from above. No way this is Newton's method. And I'll tell you, there's something else from a practical point of view about Newton's method that makes sure that this is not Newton's method. And that is, Newton's method is very, very fast, especially on a function like this. In fact, you tend to double the correct number of decimal places at every iteration of Newton's method. That's fast. This, if you notice, you have to work harder and harder just for that next decimal place, right? This is very, very slow. So from a math, if you're into doing computational stuff, this is a really, really cool parlor trick, but it's a very poor way to actually get an estimate because it's so slow, right? So,
Jim, a question.
Yes.
When you're doing Newton's method, if you're doing it by hand, you have to do a lot of divisions.
That's correct.
How does the effort for doing all of those divisions to get those doubling of the number of digits each time, how does that compare to the fact that you're not doing very much effort each digit here?
Well, I mean, actually, the amount of division that you're having to do here is actually growing quite a bit. And you're right about the Newton's method. Every time you do it, you have to sort of divide bigger and bigger. Well, actually, I'll work the square root of 3 again. I'm going to show you another algorithm. I'm going to show you Newton's method. But it depends on what you want, because if you just want fractions, Newton's method is also kind of fast too, if you can work through the fractions quicker. As far as actually analyzing how fast this is compared to this, anybody that's going to do something in the computer is going to do this because it requires much less iterations to get those extra decimal points. But as far as how much computational effort, I really don't know. I'd have to figure that out because I'm not an expert on that. Let me show you another algorithm, speaking of which. So I'm going to skip up. But yeah, but thanks for that. Any other questions on this old square root algorithm? Oh, I do want to say one more thing about this before I move on. Anybody know where this crazy crap goes where I put the digit in here and I move the thing up and all this, I double this and then add a blank out there? What is it? Notice what I'm doing is I pull this down in pairs, right? Remember how I said that? So instead of pulling every 10th decimal place, I'm pulling every 100th decimal place, right? And 100 is the square of 10, right? So basically the square root algorithm, pulling things down in pairs like this is basically sort of reverse engineering the square root, because what you're going to do is square this to get this. And so basically pulling this down is basically pulling every next decimal down, because like I said, the square of a 10th is 100, right? What happens if you take x, so if you pass from x, what happens if you square, well, actually, let me do it this way. Because every time what I'm getting is a new decimal place, correct? If you square 10x, you get 10x squared. Right? What happens if you square this? Or, you get 100x squared. There we go. You get 100x squared plus 20xn plus n squared. This is the new bit. The 10 comes from moving this over 1, multiplication by 10. Doubling it comes from the 2 factor in 20. And then what are we doing? We're now multiplying by this number right here. There's your n squared plus 20x. There's your n squared plus n times the 20x. And the 100x squared is just along from the right from the previous. Now, let me give you sort of I did this one time because apparently I had no social life, but I was sitting around and I figured out how to do this with the cube root as well. You can up this algorithm and find one for the cube root. You don't want to do it. It is an unholy mess, because instead of having to deal with this, you now have to deal with plus n cubed, which is 1000 x cubed plus 300 x squared n, right? Plus 30 x n squared plus n cubed. And you've got extra terms in here to deal with. So there is an analog for the cube root or the nth root as well, but it becomes even more unwieldy than this one. Okay, any questions? Okay, so let me go back to this other one. This is the Babylonians actually had a little trick for approximating the square root of a. So this is we're finding the square root of a. Now, I think this is really kind of cool because this predates calculus. Biology predates calculus. Well, what they did is they started off by they just estimated, right? Like maybe you want the square root of 7, for example. Maybe I'll start off with 2, right? Just an estimate. And they got successive estimates like this. Isn't that right? Yeah. So what they did is they took their estimate and they took a divided by their estimate, whatever the square root was they're looking for, figured out this, took half of it, and that's their next step. And they continued to improve this however much they wanted. And in general, xn plus 1 is 1/2 xn plus a over xn. You can continue doing this forever and ever. So for example, in the Babylonian algorithm, if we wanted to give a shot to say square root of 3, I'll write down the first few. I'll estimate, right? Actually, you can estimate just about anything you want as long as it's strictly greater than 0. Let x1 be my first estimate. Then x2 is going to be 1/2 of 1 plus 3 over 1. And of course, there we go, it's 2. Okay, so now I'm estimating, I started with estimating square root of 3 by 1, and now I'm estimating by 2. So I've wasted my time a little bit, but it gets more interesting after this. 2 plus 3 over 2. And so that's going to be 7/8. Oops, let me see here. Is that right? Or 7/4. There we go. And x4 is 1/2 of 7/4 plus 3 over 7/4, which is 12/7. And let's see, that's 48. That's 97.56 or something like this. Right. And you can continue it like this, but let me point out that by the time you get to 97.56, let's see here. Oh, yes. By the time you get to 97.56 here, what we've got is 1.7321. So that's correct, at least up to the third decimal place, just after a couple of quick fractions there. I think it's terribly amazing that they came up with this, because this is actually, this one actually is Newton's method, and this one goes much quicker than my old-fashioned algorithm.
Jim, do we know how they came up with this?
I do not know that answer. I don't know that.
I've just checked in a couple of history of math books, and it doesn't seem to get mentioned.
What, how they did it, or the Babylonian?
How they came up with it?
Yeah, I don't know the answer to that. My familiarity with it is it was a problem I saw in a calculus book somewhere, because it actually is Newton's method, right? Which Neil's question is very on point, because the Babylonians came up with this before there was calculus, right? And they just, I guess they sort of noticed that this pattern seemed to get closer and closer. It's terribly fascinating. But this one, again, if you notice, this one comes in from above, just like Newton's method. And actually, if you go through Newton and do the formula here, this formula is exactly what you get when you apply it to the function f of x equal x squared minus a, in this case, x squared minus 3. Okay, any questions on that? So the way you show this one's true is, of course, you got to do a little calculus, but I don't know how the Babylonians did it. I used to wonder how the ancients knew formula for volumes and things like that without really the calculus either. That always kind of amazed me. Here's another math trick that one of the most interesting talks on my Vita is I was actually one of the main speakers at the JCL convention many years ago. The JCL, if you're not familiar, is the Junior Classical League, and it's the Latin kids. It's all the people that are interested in Latin. So these were high school kids, and I was asked to give a talk, and I gave a talk on the mathematics of Roman numerals, and the mathematics of Roman numerals are very, very bad, right? As you know. They've got they've got the crazy stuff in Roman numerals with the 1, 5, 10, 50, 100, 500, 1,000. Sometimes they would put bars over the top of them if they wanted to mean multiplication by 100, like in bar meaning 1,000,000. And actually, most people think that this is 4, but that was actually a creation of the Middle Ages. Actually, the ancient Romans actually did 4 that way. They actually did 4 lines. This one made it even worse, right? Because what you have is you have 5 take away 1 in the wrong order, and if you start trying to add these things up, there's associativity problems, and it is a terrible, terrible system for adding. You can do it if you're careful, especially if you did what the ancient Romans did, instead of trying to put this IV or 90 by XC or whatever. You could do it, but it's terrible. The question is how do they multiply?
Mm-hmm.
I mean, the Romans had to multiply, right? I mean, they were famous for being engineers, and engineers have to multiply. So how do they do it? Well, here is a Roman algorithm for multiplying 2 numbers, 2 integers. And I will not write this in Roman numerals, but Roman algorithm for multiplying we'll say 2 positive integers. The Romans actually didn't really represent 0. So what they would do is you start with 2 integers, A and B, the integers to be multiplied. So what they did is you made 2 columns. One column starts with A, one column starts with B. And in every successive column, in each row, each successive row, left row, input 1/2 of previous row. Drop remainders. In right, double each. Well, let's see. And let's see. In each successive right row, double previous. And you do this until terminates at row with 1 in left. So you end this so every time you build another row, you have this, double, 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 and you end when you get a 1 over here. Product AB is sum of entries in right column corresponding to an odd on the left. Odd entry in the left. So for example, let's actually do one of these things. So this is where the Romans dug on their multiplication here. Whoops.
Jim, did you know that multiple cultures have discovered this algorithm? This is also known as Egyptian multiplication and Russian peasant multiplication.
Correct. Yes.
Peasant multiplication?
Mhm.
Russian peasant multiplication.
So they wouldn't give them the real multiplication, so the poor peasants had to figure out something on their own, right? So for example, let's look at 23 times 30, for example.
Sorry. It froze.
So we make new entries by, let's see, we have this and drop remainders, right? So half of this is 11, and we double this. Half of this is 5, make it 1, double this. Half of this is 2, so notice this will go down pretty fast. 1, double this, this is a 296. Half of this is 1. And double this, and this is 592. Now, what we have to do is add up the stuff, because the Romans could add up the stuff that's in the right column that corresponds to an odd entry. So that includes the 23, that's odd, and that's odd. And let's hope this works out right. So you should get 37, 74, 148, and 592, which is 21. That look right to you guys? 851. So this is really kind of a neat little trick, and it seems kind of crazy. Why does this work? Right? I mean, this seems like just crazy. I mean, you have this every time. You have to drop the remainders. What's that all about? Meanwhile, you double this. Huh. Why would such a thing work? Well, let's kind of sketch this out a little bit. So here's a sketch of why this works. If you write A equal A0 plus 2A1 plus 4A2 plus 2 to the K AK, where each AI is equal to 0 or 1. This is basically the base 2 decimal expansion of the integer A, right? You can write, in fact, you can write every integer uniquely in its base 2 decimal expansion this way. Just look at the powers of 2, and your coefficients are less than 2, so they're either 0 or 1. Right, so for example, if I had 2, then A0 will be 0, and A2 and higher will be that, and A1 will be 1, right, so forth. If you write B, two. So you start the columns like this. Oops, 281. This is certainly not a formal proof, but B0 plus 2B1 plus 4B2 plus 4 to the M B sub n.
2 to the M, dear Jim.
Oh, yes, thank you, thank you. Now, let's suppose that A0 is 1, because it's either 0 or 1. right? That would correspond to an odd entry, which means that this would be something that you add up, right? So effectively what you've done is it's 1 times this. So basically what you're doing is using the distributive law. 1 times this, right? Well, now, what do? You divide this by 2 and you drop the remainder, right? Well, your remainder is either going to be, well, your remainder is going to be 1 if this is 1, and it's going to be 0 if this is if this is 0. And so what you're going to get when you have this out, dropping the remainder, is A1 plus 2A2 plus 2 to the k minus 1 AK, right? And you double this, so this is 2B0 plus 4B1 plus 8B2 plus 2 to the n plus 1 BN. Now, if A1 is 1, then you add this up too. And that's basically what that means is this thing was live and you've distributed it in the second part. If A1 is 0, then you move on, but then you're not worried about anything until you come. Notice that we're stripping off the power of 2 here and throwing it over here. And basically what it's doing, why do you add it up only when it's odd? Because you count down, and every time you see an odd, what that means is that this term was live, right? And so it needs to be added to things in the distributed property. So this is kind of a neat little algorithm, and it's not clear just when you write it down why it works. But when you look in the base 2 decimal expansion, this should give you exactly what you want, because basically what you're doing is you're doing the distributive property, and the division is just sort of dropping it down every time and seeing what you're getting when you distribute this through. Okay. Any questions on that? Yeah, that's kind of a neat thing that, again, I don't think is obvious work. I wanted to throw in something that's called the Weierstrass substitution. I am, as some of you may guess, a bit of a lover of the calculus. I think calculus is one of the greatest intellectual accomplishments of us as a species of human beings. It is an amazing piece of work. Unfortunately, every time I hear about the AP syllabus, I just want to cry. I was talking with some friends that are high school teachers, and apparently they have been sort of phasing trig substitutions off the AP syllabus, which means sometimes they aren't taught. But you guys remember this kind of thing, which are trig substitutions, right? So this is an integral that it's not really clear what the antiderivative is until you do the substitution x equals tangent theta, right? And what it does is this turns this thing into, well, and of course, dx is secant squared of theta d theta. And this turns this into the square root of secant squared of theta, because tangent squared plus 1 secant squared times secant squared of theta, d theta. And so this is secant cubed theta, d theta. And before you do this sort of thing, there's always a section in the trig, in the calculus books where they teach you how to do trig integrals. This one, for example, you can do by parts, right? If you know what the antiderivative of secant is, which is usually taught in that section as well. And so to be able to integrate things like this, you need to be able to do trig functions, right? You also learn, or at least you used to learn in calculus, how to do partial fractions. That is, these kind of things, right? Now, how do we do this? Well, for this one we don't, it's awful. But it can be done. There's a big theorem that's actually from Brother Gauss's thesis, I believe. And basically it boils down to this. If you have any real polynomial, like these animals we have up here, any roots that are not real must occur in complex conjugate pairs, right? This is kind of a familiar thing that probably many of you have heard of, maybe since the days of high school. You saw this in like the quadratic formula, right? If you didn't have real roots, they had these conjugate pairs things, right? A consequence of that is there is no irreducible polynomial over the reals of degree more than 2, right? If it's degree 3, it's got a root. If it's degree 4, it may not have a root, but if it doesn't, it splits into irreducible quadratics. And it may not be so clear what this is, but if you know a little number theory, or a lot is helpful, you can actually factor this into 2 irreducible quadratics, right? And so now you can split this up and you can write it as this squared and so forth. And you've got this thing in partial fractions. It's basically linear algebra, where you would write the decomposition of this as, you would rewrite this thing, x, let me write it out here, x squared plus radical 2x plus 1, x squared minus radical 2x plus 1 squared, x squared plus 1 squared, x cubed. And hopefully this doesn't take you back to, some kind of terrible memories like the Prince of Tides or anything like that. But let me remind you that this thing, even though it looks like a total mess, you can rewrite this in the partial fraction form, ax plus b over x squared plus radical 2x plus 1 plus cx plus d, x squared plus radical 2x plus 1 squared plus ex plus f, x squared plus radical 2x, rather be minus now, plus 1 plus gx plus h over x squared minus radical 2x plus 1 squared plus ix plus j, x squared plus 1 plus kx plus l, x squared plus 1 squared plus m over x plus n over x squared plus p over x cubed. Do you guys remember this awful partial fractions form, right? And so you can figure out what the coefficients have to be, right? After all, it's only 15 equations and 15 unknowns, right? You have to figure out what A through P are, excluding the O, and you will get the coefficients you need, right? Awful mess. But once you've got it figured out, all these integrals can now be done. This one right here, you can complete the square and do a trig substitution. Same. And in fact, if you're really lucky, some of these might even turn out to be log sub. If you get really lucky with the constants, you might have a log substitution to do. But worst case scenario, trig substitution. That's a log and an arctangent. Trig substitution, m log x minus n over x minus 1/2 px minus 2, right? Plus constant, and there you go. So the moral of the story is with partial fractions here, in theory, I can do anything. I can do any rational function, provided I can factor this. And of course, factoring these polynomials is not always a trivial part of it, but in theory, you could at least get some approximation for it, right? Now, here's the question. And this is something that's, you can find it in exercise in most calculus books, but if I asked you to do that problem, well, you would probably say u equals sine x and u equal cosine x dx and be done with it, right? Easy peasy, lemon squeezy. Well, what if I asked you to do this? Well, you could actually do that one. Let's do this one. 2 cosine x plus 1 dx. Right, u equal to the bottom's not going to work. This is a mess, right? Now, if you think about your techniques, right? Really, u equals bottom's all you got to go on. Parts, no way, parts going to work very well with this. So what do? Well, there's a terribly clever trick called wire stress substitution. There's a version of this with trig functions and also with hyperbolic trig functions. I'll just do the trig functions here. And this will always turns quotients of trigs to quotients of polynomials. And with the quotient of polynomials, big smile, because as I explained earlier, in theory, we should always be able to do quotients of polynomials, right? Because it's partial fractions. And this substitution is something that's really, really kind of way out there. Try this substitution. T equals tangent x over 2. And this thing will always work. It always turns quotients of trig functions to polynomials. And probably the most important thing I can show you here is why it works, right? So here's the idea. What do I have in the original integral? I've got cosines and sines. Maybe I would have had other trig functions that I want to get rid of somehow, right? And so here's the idea. I'm going to call this angle x over 2, and t is the tangent of it, so it looks like this. And so my hypotenuse is this. And this depends on some really cool trig identities, right? Let me point out that sine of x is 2 sine x over 2 cosine x over 2. And these things, sine x over 2 and cosine x, can read right off of this triangle, right? This is 2, the sine of x over 2 is t over the square root of t squared plus 1, and the cosine is 1 over the square root of t squared plus 1. So I get 2t over 1 plus t squared. Notice those square roots cancel out, and that really kind of saves me here. Cosine x is the same thing as cosine squared x over 2 minus sine squared x over 2. And again, I can read this right off of here. Cosine is this, so I square it. And sine is this, so I square it. So I get 1, I square it. 1 minus t squared over t squared plus 1. Now, in U substitutions, there's always that business about the dx and the dt, and oftentimes that's the reason why certain substitutions that you try fail. However, notice in this case that dt is secant squared x over 2 times 1/2 dx. And so this means that 2 dt over secant squared x over 2 is dx, and this is 2 dt over tangent squared x over 2 plus 1. But lucky me, that's t. So I get 2 dt over t squared plus 1. So this is a miracle because, I'm sorry, that's dx. There we go. Because your dx is a quotient of two polynomials. Your cosine x and your sine x are the quotients of two polynomials. And so every trig function that you can form, since they're quotients of sine and cosine, must also be quotients of polynomials. So for example, in the example that we have up here, I'll just write this down really quickly. If you're to do the Weierstrass substitution, we would get something like, after the substitution, you get 1 minus t squared over t squared plus 1. Sine is 2t over t squared plus 1 plus 2, 1 minus t squared over t squared plus 1 plus 1. And then my dt, which is, or I'm sorry, my dx, which is 2 dt over 1 plus t squared. Now, that looks like a mess, and it is a bit of a mess, but it's doable. Because, for example, this becomes 1 minus t squared, 1 plus t squared, times 2 dt, and the t squared plus 1 sweeps out the bottom, so this is 2t plus 2 minus 2t squared plus t squared plus 1. And so this is going to be 2 times 1 minus t squared dt, and t squared plus 1 again, times whatever this mess here is, which is, I guess, 3 plus 2t minus t squared. And actually, 4, 12, 16, this actually factors nicely. So you might actually get an interesting answer. You're going to get an answer that involves, your antiderivative will involve tangents of x over 2, which is really, the antiderivatives often look strange. And you can actually take the original function cosine x over sine x that you can easily integrate and do the Weierstrass, and sometimes you can get interesting sort of trig identities out of that. So actually, I've got more of these, but I'm out of time. Maybe sometime in the future, I'll talk about determining divisibility of different bases, which is kind of cool. There are tricks. We all know how to tell very quickly if something's divisible by 2, 3, 9, 5, but there are also tricks for 11, 25, 27, 37, 101, and so forth, that have to do a little bit with number theory. Okay, I think that's good for now. Thank you all for coming out this afternoon. Let me see here if I've got any chat questions here. Oh, I'm gonna have to stay on and read those. Okay, any questions? Any questions? Okay, well, if there aren't any, thank you all for turning out. I hope you all stay safe and have a great weekend. And oh, let me also say, I'm going to send out an announcement pretty soon. You've got the math end coming up at the end of the semester. We're going to do it the same way that we did last semester. It's going to be virtual on Zoom, but I'm going to put a call out. If any of you are teaching, be sure and tell people about this. It will be Saturday after the classes end, so that'll be the 24th, I guess. And if you'd like to participate, I'd love to have you. So You all have a great weekend, and I will see you all soon.
I love that quote from Ifra. A wealthy German merchant in the 15th century, seeking to provide his son with a good business education, consulted a learned man as to which European institution offered the best training. If you only want him to be able to cope with addition and subtraction, the expert replied, then any French or German university will do. But if you're intent on your son going on to multiplication and division, assuming that he has sufficient gifts, then you will have to send him to Italy.
That's pretty good.
Isn't that a wonderful quote? Have you seen? Oh, go ahead.
No. Have I seen what?
Japanese multiplication.
I'm sorry, you kind of broke up on me. Seen what now?
Have you ever seen Japanese multiplication?
No, I don't think I have.
Google it later. It's worth looking it up.
Japanese multiplication. I will do that. All right.
It's very graphical. You will love it.
Okay. All right. Sounds good. I'll look that up tonight if I got a chance to do that.
And good luck with you and your family getting the vaccine.
Yeah, that's right. I'm on. Actually, I think my wife will be especially excited about that because I mean we've got the 2-year-old and she's a first-time mother, so she's more nervous than she needs to be. But you understand that, so.
Oh, absolutely. Is she teaching with Clemson at the moment?
She is.
So she's eligible too right now.
Yes, she is. Yeah. Oh, yeah. She's okay. That sounds good.
Because it's going to get, I suspect, a bit more difficult to find doses as of Wednesday once everybody's open to it. So you might want to call Ingalls, which is partnering with Clemson at the moment, in the morning and say, do you have any slots open in the next few days? Because the folks who are coming into eligibility on Wednesday can't actually book until Wednesday. So there should be some slots open in the next few days.
Okay, I appreciate. Actually, I'm going to call my wife and let her know that. So I appreciate that very much.
And good luck with it.
All right.
And I'm looking forward to seeing you in person so we can riff on some of these ideas. Yeah. Did I send you a copy of the paper we did with Sylvia and Evan and Killian and Catherine Kenyon?
I don't know if you did or not. I know I've seen it. I thought that maybe Evan had sent me one at some point. Why don't you send it to me again?
Okay, I will. It's my 4th paper in the monthly. It got accepted in January, and I actually got my 5th paper in the monthly accepted yesterday.
Nice.
So I'm 5 for 5, which is it's a 10 to 1, 9 to 1 rejection rate.
Oh yeah. I talked to Scott Chapman about it, and it's about 10%.
So I figure I'm batting about 100,000 to 1.
That's right. Sounds good. All right.
Okay. Well, have a great weekend, Jim. That was a lovely talk. I had seen everything. I had not seen the Weierstrass substitution.
Oh, okay.
Before. By the way, Weierstrass does not have a U in it.
Oh, I see. I did put a U in there. Okay, I did not know that either. Yeah, I guess I was. It doesn't have a U in it, huh?
No, it's Strass, like street, as opposed to Strauss.
Okay. Yeah, is it ever spelled wrong in books? Like L'Hôpital is spelled like 2 different ways, right? Some people spell it like I just said it. Some people spell it with the S in it, right? And I've heard people get really angry about it one way or the other.
Yeah. No, it's definitely no S in L'Hôpital. The French word for hospital is hôpital, and it's spelled without an S. And of course, L'Hôpital didn't do the proof.
I heard somewhere some apocryphal story that L'Hôpital actually paid somebody, some famous mathematician, get credit for that rule or something like that.
I don't think it's apocryphal. I think it's actually fairly well documented.
Oh, wow.
That he was basically the funding agency for a decent mathematician.
So he wanted a little bit of the glory, right?
Yeah. It's like we put in the papers. Thank you to the NSF for funding.
Right.
But I forget who it was. Let me see. I happen to have this right in front of me. It's Strauch's book. L'Hôpital, 1902. So L'Hôpital wrote a treatise on the analysis of conic sections. So he was a moderately decent understander of mathematics and popularized it. In 112. Yeah, he wrote a book, The Analysis of the Infinitely Small, quote, under the strong influence of Johann Bernoulli, who had for a while tutored him. This book, for a long time unique in its field, contains the so-called rule of L'Hôpital for finding the limiting value of a fraction whose terms both tend to 0, footnote 19. This rule was communicated to L'Hôpital by Johann Bernoulli in a letter, which only recently has come to light. So it was Bernoulli, Johann Bernoulli.
Okay, well, that's good to know.
One of the lesser ones. If you don't know, I've got several history of math books, if ever you want to peruse some of them.
Okay.
They're more decent ones than Eric Temple Bell,
Right.
who gets so many things wrong.
Right. Yeah.
And some of them don't stop at Newton.
Right.
So
All right.
anyway, that was a lovely talk, Jim. Thank you.
Well, thank you, Jim. Have a good weekend.
You too. And good luck getting the vaccine soon.
Yes, thank you.